invitation. I'm very happy to be here. The labs, the whole building, and all what you guys are doing is incredible. So I'm very happy to visit here. What I will present today is something about the budget of volatiles, from where, when, and how water came to the Earth-Moon system. This is work that I have done mainly with Eric Howdy from Carnegie Institution of Washington, Mark Rutherford from Brown University, and James Van Orman from Case Western University. Essentially, in the outline, we will have motivation, why we are doing this, the rationale for studying the moon and volatiles, the consensus of the moon volatile budget before we start with our results and explanation, and then the conclusion. So just to give you a background, most of you probably know these things, but just essentially, if you see the plane of the ecliptica and you see this is the orbit of Jupiter, Saturn, Uranus, Neptune, essentially the material that form the terrestrial planets should be mostly what they call asteroid type S. Think of a type S as silicates, devoid of volatiles. They are too close to the sun. All the asteroid type C are after Jupiter or after, which is called the snow line, the point at which you will have the condensation of water in the nebula. Always if you think of the nebula that is essentially static. So then they said most of the terrestrial planets should be devoid of water. Well, we have a problem, it's clear. And then the question comes how that came to be, why these terrestrial planets have water. And one way is to study the Earth, but the Earth is very dynamic. I will not go on this, you know it. So because it's very dynamic, it's very, very difficult to specifically state when the water came to the Earth. Something that could be on the surface because of the subduction. Think of this of composition, think of it of temperature. There was a nice model that Van Keken did, and it's nice to illustrate. And so it could have come quite late, like 3.9 billion years or so, and then you can say, well, okay, water was here, and then you will get an idea. So one way to approach it in a different way is just not to work on Earth, but just to look at the moon. Essentially, why? Because the moon, you can think of it to be essentially frozen. The interior of the moon was essentially isolated within the first few 100 million years since their formation. That means that if there was water in the interior after the first 200 million years, then through the lavas you can see whether there was or not. Why is it important to study volatile? Well, many of you work on volatile, so it provides information of the condition of planetary formation, affects the dynamic of planetary interior, modify the mantle and melt viscosity, influence core segregation and longevity, decrease the melting point of solid, affect the mechanism of lava eruption, and is fundamental for the origin of life. So we know that our observations are indirect. Essentially, we look at the composition of the lavas. This is a fire fountain eruption. You know this, it breaks off, the material that it's breaking off, essentially think of this as chip of melts that are flying around, and then they quench, and then they deposit. Then the Apollo mission, this is just to illustrate what happened in the eruptions of the moon, eruptions that are called fire fountain, and then they collected by the Apollo mission the samples. The reason that these are good for us, well, the first is glassy, so it's easy to analyze by the ion probe for the volatiles. You can have, I will give you several examples, but this is Apollo 15, and you can see the green glasses, Apollo 17, what they call the orange glasses. You already can see that there is a difference in composition based on the color. The green is mainly given by the iron, the orange is given by the titanium. So that means that in most cases, these and these essentially represent a different type of interior or reservoirs within the moon. Why also they are important? If you have magnesium number, you know this is an expression of how primitive, how unmodified are the lava compositions. These are most of the mare basalts, the fields that you see. These are the composition of the glasses, and you can see that the composition of the glasses, this is titanium versus magnesium number. The titanium, you need to think that these groups represent different sources, and most of the glasses seem to represent the most primitive lavas or samples that we can get from the interior of the moon. When people did multiple saturation experiments to see from what depth they came, essentially you need to think of around well, 250 to 500 kilometers within the moon. So these things came up from the interior of the moon, they were erupted, they quenched, they got deposited, and then the Apollo mission collected. Okay, previous studies, yes, people have done this. They did it, the last big study on the volatiles for moon samples was done in 1973, which was a compilation. The Apollo mission was run from 69 to 72. By 73 was the last conclusion of how much work there was. And it was mainly a review paper, I think, is Epstein and Taylor, which is very good. And essentially what they found, they took the glasses, this is a bit different. They took the glasses, a group of glasses, they put in a mass spectrometer in vacuum, and then they did step heating, and they see the molecule that came out and the isotopic composition of the molecule that came out. And then they found out that first, there was hydrogen as a molecule, H2, and the isotopic composition was very low DH, so they said this is solar wind implantation. Essentially, these lie on the surface, the solar wind implanted. The implantation goes up to 100 nanometers from the surface of the glass bead. The second thing that they did, they found a molecular water. But the isotopic composition of the molecular water that they found was essentially the same as the isotopic composition of the water in Pasadena. So they said, okay, this is contamination from the lab. And then that's the story. Essentially they said, what we see is contamination from the lab, water from Pasadena, and hydrogen from the solar wind implantation. Therefore, the moon was bone dry. And this is 1973. So that's not what killed the whole thing. What actually killed the whole thing is in the 1980s. It came the model of how you form the moon. And we will explain this. So by the giant impact, so for 40 years, we thought that the moon was completely bone dry. The reason why this worked is this is just a model that Canap did a long time ago, but just represent pretty well. This is temperature. I don't know if you will see it. This is 7,000 Kelvin. I think that this is around 3,000 Kelvin. So you can see the temperature is very high. The protolunar disk is all this material, has low gravity. If it has low gravity, the volatile element, especially hydrogen, will escape. And then they said with this temperature and hydrogen is lost. Did they measure in 73? They said yes. They found only implantation for solar wind and then contamination. So this was the killer. That's the nail that closed and said, okay, there is no water or volatile elements in the moon, especially hydrogen. When people did models, and you can see that this is not 1973, Alvarez still think that this is the case. This is 2014. This is normalized to chondrite, so essentially think of this, the most primitive solar nebula. The Earth has depleted in volatiles, which is the blue, and then the red represents the volatile composition of the moon. Okay? And you can see that between the moon and the Earth there is a 1,000 time depletion. That's what Francis Alvarez and many others think even today, but also people thought in the past that there was no significant amount of hydrogen. So that's the consensus when we took the work. This is the work that we started around 2008 or so. I will give a little bit of the analytical technique, why this is important for this. We will present the first observations of unequivocal concentration of indigenous lunar water, carbon, fluorine, chlorine, and sulfur. How we try to estimate the volatile budget, there may be some errors, but it will not be as large to accommodate what people think that is 1,000 times more depleted the moon than the Earth. Why we believe that there is a difference in the discrepancy, what people did before and what we are doing now, where the difference is, and from where, how, when the volatile came to the Earth-Moon system. The first thing, something that we did very different from previous people, for example, Epstein and Taylor, that they put a group of lunar glasses together. What we did is we will take a single glass, and then with the ion probe, I don't know if you're familiar, many of you are, some of you not, but essentially what you have is, you have a sample here, 300 microns each bead, not a lot of bead together, but one single bead. This is 300 microns. You put the bead here. In vacuum, you have a gun. It could be cesium or oxygen gun. It ablate the sample. It ionize. You put it through electrical current. You separate the elements that you want to measure, and you measure. All this is in vacuum. The beauty of this is that you can analyze at very, very small spatial resolution. With the nanosims, you can see that we make a 10 micron area raster, and we collect within the 4 micron center. For the other, which is the other type of Kameka 6F, you can do a 30 micron raster, and you collect within the 10 micron center. We pre-sputter to avoid any contamination from the surface by 6 minutes. And then you can see the detection limits are pretty low. 1 ppm for hydrogen, 0.06 ppm, you can say 1 ppm for carbon, 1 ppm for fluorine, 1 ppm for sulfur and chlorine. And then the accuracy that we get the measurements, you can see between 13, 17. Chlorine is probably the one that we have the largest uncertainty, but most of them tend to be within the 10% or so. This is just to calibration using glasses. So one big difference then is we analyze a single bead, not all the bead together and the bulk sample composition, but we put a single bead. This is an SCR image. This is the lunar glass, and here you have 2 spots that were done with the 6F, the large spot, one to measure the volatiles, one to measure the trace elements, and we did it in the middle of the glass bead. And then what we did is with the nanosim, we did a transect. The reason that we did the transect on a single bead is because if it's contamination, we expect that you have higher concentration on the border and lower in the center. But if it's degassing, meaning the hydrogen was inside and is trying to get out, I should see higher concentration in the center and lower in the border. And that's what we did. So, and what we found is that the core will have higher concentration, the rim will have lower. Not only for water, did it for chlorine, for fluorine, and for sulfur. And you can see that the difference between the low value and the high value seems to be larger for hydrogen, decreases for the chlorine, decreases for the fluorine, and then decreases for the sulfur. So that told us that essentially what is controlling the variation is essentially the degassing, but the degassing is happening by kinetics. Essentially, the hydrogen is trying to escape from the center, through the glass, get to the surface, jump into the gas. And because hydrogen diffuse really fast, we can apply the diffusivities and a model, a simple model of a spherical geometry, where the diffusivities that we have are for basaltic compositions, mostly for Earth compositions. And we took the liquidus temperature, and then what we did is try to say, well, for how long during the eruption you have the bead, the fragmentation, the bead will fly into vacuum, and as it flies, it degasses kinetically, and then it deposits. I'm not considering with the calculation what produced the fragmentation. I need gas to produce the fragmentation of the bead. That we cannot tell you. But we can tell you within the bead how much this was degassed in the time from eruption to quenching. And that time can be calculated by looking at the size of the pyroclastic deposit. So we did the modeling, and what we found is that the hydrogen was 98% degassed, chlorine was 57, fluorine was 45, and sulfur was 20.
But
so
when you do that, you have to assume the inside is not degassed, or no?
No. You just, what we did is trying to match, given all the constraints, the size of the bead, and all the constraints that I tell you, to what will match the 4 elements at once, what will minimize the chi-square,
okay.
And then that's the values that we took. Okay? And that's very important, because many models can match the hydrogen alone.
Sure.
But very few models, and I can show you if you want later, many few models can match the 4 of them together. So the key point that I wanted to make is that we said the best concentration to explain the initial concentration of water was at around 750 ppm. From no water to have 750 is like mid-ocean rich basalt. That means, at all things equal, if mid-ocean rich basalt has this amount of water, if they are produced, the lunar glass is similar to the mid-ocean ridge by the same extent of melting, let's say, then you can say, well, okay, the concentrations in the mantle of the moon should be roughly equivalent to the concentration of the mantle that you see in mid-ocean ridge. And we said, okay, a minimum, at the 95% confident, a minimum should be 260. The second thing that we did, these are individual. Each one represents one glass now. So each one of these points represents one glass, analyzed in the middle. But the glasses have different sizes. So then we overlap the cross-section that we did in one single bead with the total variation that we see in many beads analyzed in the middle, and we said that the trends are the same. What that tells us is that the trend that we see displayed by many of the glasses is all consistent with the degassing process. Then it became the question, well, what you're presenting is a model. You're telling me that there was 750 ppm, but that's a model, and we all know models are models, and depending on the variables that you use and things like that, we said, fair enough. So the question that came up is, what is really the initial concentration that we have in there? And then, what is the distribution? Meaning, are these samples that you are working with representative? So we did it only on something that I forgot to tell you is, sorry, the colors will tell you something about the content of titanium. The very green, meaning the very low titanium, the orange will give you the high titanium, and then the intermediate colors will give you different groups. And then I will show something that answers this and this question. How representative? For the initial, well, the only thing that we can do better than analyzing the glasses was to analyze the melt inclusion. Essentially, it's when the olivine grew up from the glass, it trapped inclusion. Because it trapped it at pressure, essentially, it's the most representative things that you will have from something that is primitive in regard to the volatile content, although some of the hydrogen could diffuse out by diffusion. In any case, this gave us the possibility to have the most primordial concentration of volatile that these magmas had, because they are trapped, essentially locked within a crystal. When we look at the composition of this, what you see here is fluorine, sulfur, chlorine versus water. These are the glasses outside. These are the melt inclusions from the moon. The gray field is for you to have an idea what are the concentration of volatiles in mid-ocean rich basalts. And you can see that the melt inclusions that we see on the moon seems to have very similar to the concentrations of volatiles that you see in mid-ocean rich basalts. Therefore, the concentration, this is not a model, this is an actual measurement. So now we can say, well, it was not to a 750 ppm. It's essentially the concentration could go up to 1200 ppm measured. So that, in some ways, settled some of the questions. And the other thing that we did is to measure carbon. And this is a little bit overloading, but the most important things when you measure carbon and hydrogen, you can do a model of degassing that will tell you the fraction of the gas, the fraction of water and CO2 that there is in the gas, and the pressure at which that melt was in equilibrium with that gas. And you can see, for example, most of the glasses, these are the melt inclusions, and all this field that you see here at low carbon seems to be the glasses outside. The melt inclusion shows the variation is not much. It goes from 4 ppm to 0.5 ppm. This is around half a kilometer within the moon pressure. But I think that's something that, and this is an expansion of this area in here. But I think that the most important thing to say is this difference. If you put in log-log, just to see this better, you see that the melt inclusion seems to show a significant variation in the carbon without significant variation in hydrogen. But the glasses seem to show a very, very strong variation in hydrogen without significant variation in carbon. So what this is telling us is essentially two types of degassing. An early type of degassing, when the magma is moving up. There is a degassing as the magma is moving up. It's being trapped at different levels by the melt inclusions. And then it represents what we call either a Rayleigh or an equilibrium degassing. But then when it reaches this depth, around 500 meters below the surface, the magma got enough volume of gas that exploded and then the beads now are flying out, and now the degassing happened by kinetics, meaning from the center of the bead to the surface, whoever can move faster, that's the one that will degas the most. And what you see is now, in this case, the one that is changing the most is hydrogen, because of the diffusivity. Here, the ones that is changing the most is carbon, because of the solubility. So two mechanisms of degassing that explain the trends that we see. Just to show that we see the same in a single bead, these red points here represent a cross-section within a bead. That was a yellow. And here you have the cross-section, you have the carbon, you have the hydrogen, and you can see the cross-section within the bead. Here you have the colors represent intermediate, the yellow, the green, very low titanium, and the orange, very high titanium. How representative? Well, the best thing that we can do is try to get as many of the samples they collected from the moon. They are collected from where the Apollo mission came. They are limited geographically, but that's all what we have. And when you look at that, you can see that all of them seem to have significant variations in volatiles. All of them have water, so you have, this is Apollo 15, what they call yellow glasses, Apollo 15 green glasses, Apollo 17 orange glasses, or Apollo 14, which they don't have any color, they call it Apollo 14, that have a significant range. So all of them shows volatiles. So the best we can say, given the samples that were collected by the Apollo mission, all of them seems to have water. There is something interesting. One of the things that is interesting, you can see that because hydrogen diffuses so fast, these will tend to collapse. So there will be a diffusion very fast. I cannot tell you what was initially in each group unless I can find melt inclusion in each group. And this is the only group that we found melt inclusion. All the others, the olivines quenched really, really fast, so it's hard to form melt inclusions. But you can see that the difference in fluorine, because it doesn't degas so fast, shows difference between the different groups. So each compositional group seems to have a different fluorine content. That means that the degassing of fluorine was not enough to homogenize the fluorine, and I still see an initial difference in the fluorine content from where this magma came from. So when you look at the total, so you put the melt inclusions for the orange, so the degassing will do this. This is the trend for degassing for the sulfur. This is the trend of degassing for the fluorine. The orange glasses are here. And this is, well, you will not see it, the degassing for the chlorine. So you see the trend of degassing. This is the kinetic degassing, where mostly the water is the one that is degassing faster. But then you have a trend like this. You see it better in the sulfur. You see a difference. Green glasses, orange glasses, yellow glasses, Apollo 14 glasses that have significant variation. We think that this is mostly variation in the source. This is the variation because of degassing. There is a little bit of variation during degassing, but it's minimum compared to the initial variation that there was within the source. So we can say the green glasses have the low volatiles, the orange glasses and the yellow glasses have intermediate, the Apollo 14 glasses seems to have the highest. When we look at the trace elements of these, and these, now I'm looking at all these elements. Some of these elements are volatile, some of these elements are refractory. This is normalized to a primitive mantle composition. What you can see, two things I want to make a statement on this. First, you can see that the trends tend to be essentially flat. Okay, so you have the ones that have low volatiles have low trace elements. Intermediate, those with high volatiles have high trace elements. And that the trace elements seem to be flat. So it's a dilution effect, something that produces a dilution effect on the concentration. So what process can explain that? What process? All these elements, by the way, are called incompatible, meaning they tend to go into the melt during melting. They are all volatiles tend to also be incompatible. They tend to go to the melt during melting. And essentially what this is telling us is, well, the reservoir of these things seems to be with different levels of enrichment in volatiles and in incompatible trace elements. The simple process that people argue, and this is something that I just used the model from people that have done this, is assuming a lunar magma ocean. The lunar magma ocean is crystallizing bottom up. So they begin to crystallize olivine orthopyroxene, olivine, pigeonite, plagioclase. Plagioclase begin to get less dense than the melt. The plagioclase float, form a crust. So essentially now you're beginning to solidify from bottom up. The crust begin to fall and get thicker, and then you continue crystallizing, 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 until you leave a residual melt that is called creep. This residual melt that is called creep is because it's very enriched in potassium, rare earth, and phosphorus, is essentially this type of composition. So it seems that the variation that you see is coming from the different sources that have been either variably contaminated with the creep, or as you differentiate, you produce different level of concentration of these incompatible elements. And the dilution effect is simply that. So that will produce a dilution. This will be the most concentrated, this will be the most diluted, and then you will have a variation in between. So whether some people talk about overturn, if you do an overturn, there will be some mixing in the source, or the melts that are passing through the creep, they are contaminated. I cannot tell you what's the difference between the two, but both are possibilities and both explain the data. Now we need, yes?
On your rare earth pattern, did you have the melting fusion?
No, when I did it, we do. It doesn't look very different from this.
From the yellow.
Okay, but the errors also are large. No, we didn't see significant variations in the, if you're asking what's the concentration in the melting inclusion from the glasses, not much difference. Not something that I can tell you for sure. So using this model, using the simple partition coefficient, we try to figure out how much water there should be in the initial melt that crystallized to form these different reservoirs, and we finish with around 100 ppm. So 100 ppm, depending who you talk, but for the Earth, you can say that at least it will be a factor of 5 or so. For Earth, you can say 500 ppm water for the total Earth will be a conservative estimate using the basaltic composition that erupted on the surface of the Earth.
Can you convert us pressure corresponding to the depth? Because I don't know the gravity of the moon, so I cannot do this.
This 1/6.
1/6, so 1600 kilometers you have the olivine.
Pardon me?
The 1400 kilometers you said the olivine, right?
Well, around there. That's what the model said.
Okay.
And again, you can look at his Parmentier and Schneider. I just followed that. I didn't assume that they did a mistake. So now we need to get to the budget. And to get to the budget, one way that we did is we look at elements that behaves during melting or magmatic processes very similar to the volatiles, but that they are not volatiles. For example, water Syrian. Syrian is refractory, water is volatile. And what I want you to say, I told you that the volatiles, these are melt inclusions from the moon, these are melt inclusions from mid-ocean-rich basalt. You can see that they have the same volatile content. But the Syrian is different. The Syrian is a factor of 5 different. What that means is I need to enrich in incompatible elements 5 times to get to the same volatiles. Okay? Or I can say at the same Syrian, I have 1/5 of the volatiles that we found on the Earth. Okay? Not 1,000 times, 1/5. We did that for all the others. For fluorine, volatile versus neodymium is refractory. Sulfur versus dysprosium is refractory. Water versus Syrian that I show you. And then we did chlorine, this figure. When I did this figure, I used potassium. Potassium is volatile, but then we did it with niobium, and it's non-volatile. And again, all of them shows a difference of around a factor of 5. Okay? Not 1,000. I think that that's a very important point. So based on that, we look at the ratios that we get for the moon based on the green glasses or orange glasses, this based on the melt inclusions, this based on the model. And you can see, you have, this is the range, this is what you see for mid-ocean ridge, this is the range, this is what you have for mid-ocean ridge basalts, this is the range for the moon, mid-ocean ridge. So in all of them, you don't see a significant variation of more than a factor of 10. Not, again, not a factor of 1,000. We went a little bit further, and what we did now is, okay, we know that there is a gas that produced the breakup of the lava, big eruption. Now that gas cloud begins to condense, and it begins to deposit on the surface of the glass. So the concentration of volatiles that were lost in the gas can be recondensed on the surface, at least partially recondensed on the surface of these glasses. So how to get to the concentration that is on the surface of the glasses? Well, we use a null technique, 1976. Essentially what they did is they take these glasses form an eruption. They take all the glasses have the same composition. The only difference that they see is the difference in the grain size. So larger the grain size, surface to volume is very small. As I am decreasing, the surface to volume is smaller, surface to volume is smaller, smaller, smaller. That means when the grain size is 0, that's the concentration of the surface. And that's what we took. Using that, and so we get the sulfur in the melt inclusion, the sulfur in the glasses, and the sulfur that was deposited onto the surface. So based on that, we make the estimation of how much degassing of the sulfur was, and then we take the ratios of all the elements to sulfur to calculate how much degassing of all the elements degass. And for the elements that we had data, sulfur, sodium, zinc, gallium, germanium, cadmium, indium, tellurium, mercury, and lead, we can calculate for the ones that we have the data. For those that we don't have the data, we cannot do it. But you can see that most of these volatile elements have been lost during the degassing process. That means when these lavas erupted into essentially vacuum, they lost a lot of volatile elements. So when we go and we collect something from the surface, we measure and then we extrapolate to what is in the interior. Without correcting for the degassing, we will essentially calculate absolute minimum, what it should be. When we correct for the degassing, then we can make a better estimation of what was inside. When we do that, this is what we get. This is the same plot that you saw before with condensation temperatures, but now we normalize it not to the primitive mantle, to the chondritic composition, but to the Earth. So this is the moon, bold silica Earth, bold silica moon normalized to the bold silica Earth. And most of the volatile elements are here, except chlorine, and I think that this was a problem with the normalization, and I can explain that later, but chlorine should be around here. So what you see is most of them are within a factor of 10 compared to the Earth. So we said, okay, there is a depletion in the moon, yes, but the depletion in the moon is not a factor of 1,000, it's a factor of 10. To confirm that, what we use is very simple. We know what is the strontium isotope, the initial for the solar system. And then we know certain early rocks that form on the moon, and we get the ages of those rocks. Based on the ages of those rocks and the initial isotopic composition of strontium, we can calculate, based on what we measured on that rock, what should be the rubidium-strontium ratio. Rubidium is volatile, strontium is refractory. The same we can do for lead isotope, where uranium is refractory, lead is volatile. So this ratio is telling us volatile to refractory element. And what you can see is whatever you estimate from these lunar samples, very early formed lunar samples, you have 0.035, 0.044. The bold silica Earth is 0.089. Not that different, the rubidium-strontium from the rubidium-strontium of the Earth. That means, again, within a factor of 5 or so. For the uranium-lead, well, there is a range. You can say for the moon, people say it's 30 to around 10. The uranium-lead that we get for the Earth is around 8.5. Again, not that different from the Earth, not a factor of 1,000, but it's a factor of 5. So, therefore, then what we say, before we make an estimation what is the level of depletion of the moon compared to the Earth, we need to consider the degassing, magmatic degassing. So now, and when? To the Earth-Moon system, what we did is a fingerprint, the easiest fingerprint to to deal with will be the DH ratio, the hydrogen isotopic composition. Here it's just samples, protosolar, Jupiter, Saturn, Uranus, Neptune, Mars, Mars atmosphere, Earth, chondritic, carbonaceous chondrites, comets. So the question was where the moon was. So we measured, and the first thing that you can see, this is concentration of water, high concentration, low concentration. Most of these that you see here are glasses. These are the melt inclusions for the orange glasses. The first thing that you see is there is an inverse correlation between the DH ratio and the water content. As I have less and less and less water content, the deuterium can tend to go up. Less and less and less, deuterium tend to go up, which is consistent with kinetic degassing because the hydrogen will diffuse faster than the deuterium. So the question is, okay.
But how come slope is different?
I will tell you in a minute. The slope is different essentially because the production of deuterium also is affected by something else. It's cosmic rays. So essentially the cosmic rays come, hit the sample, magnesium, oxygen, silica break up and give you deuterium. They give you much less hydrogen. These were exposed to cosmic ray by 300 million years. This was only exposed by 30. So we needed to correct for cosmic rays before we do the estimation. Then we know that equilibrium and Rayleigh fractionation will not work because it will not give me this kinetic degassing trends. So what we did is a simple kinetic model that was done for argon a long time ago by McDougall and Harrison. It's one-dimensional. And essentially what it says is that the diffusivity of hydrogen with respect to deuterium will be related to the inverse of the mass elevated to a beta factor, and the beta factor likely depend on the hydrogen speciation. Let me show you. We don't have many constraints experimentally on this, but we did the best we could given what we had. Now you can see all of these tend to be corrected by these spallation processes, but also you can see the errors. The errors are huge. The reason that the errors are huge is because errors on the edge of exposure, errors on the production rate, how much deuterium is produced per unit time, per gram, is hard to estimate. There is a factor of 2, essentially, variation. I will deal only with the orange glasses because these are the ones that have the melt inclusions, and also because they have been exposed the least, 30 million years, to cosmic ray. This is the value analyzed, this is the value corrected, and these are the errors. As your concentration goes higher, your error goes smaller. Because the impact that you produce by the deuterium by spallation, because I have high concentration, is very small. So the best thing I can tell you is, okay, this will be the maximum DH ratio that this glass had initially. The lowest that I can get at the highest concentration, that's the maximum DH. Is that or even lower? That's the best I can do. Now, the lines that you see, this is assuming that H and D are diffusing, theoretical. The purple represents the range of possibility for diffusion when I assuming that H2 or HD are degassing. The green assumes that the degassing is H2O or HDO. That's the range. And then the blue, when you assume that the degassing is done by HO or DO. And we said, well, empirically the data seems to follow this, although there is a change here, but I cannot tell you how big the change because of the error. So in any case, the bottom line is this. This is the highest DH ratio that these classes should have. When I plot that value, all the rest, anything else is produced by degassing. This is the value for the moon. Very, very consistent with carbonaceous chondrite. Now I want you to understand, again, the same process that happened on DH ratio with what happened with the concentration. People went and measured DH ratios in sample from the moon, and they got very high values of DH. So they said, what has high values? Comets. So they said, the volatiles that we see on the moon are comets. When you see a value, it could correspond to source, but also it could correspond to process. We think that this variation that you see is not because you have a difference in source, because you have essentially a degassing process acting. When you look at the nitrogen, just to build on that, these are the comets, nitrogen and DH isotopic composition. The nitrogen was done by Marti, the DH was done by us. You can see these are the field for carbonaceous chondrite. The Earth is here, the moon is here. So that in regard to, so we said, okay, the volatiles that came to the moon should come from chondritic material, carbonaceous chondrite. Okay, so now, when the volatile was added to the Earth's moon system, the only thing that I can tell you is, okay, how quickly you can form the lithosphere on the moon. Depending on that, that will give me the limit. Meaning, I know that the volatiles were from the interior because I see it from the lavas. Now, how I have the moon completely molten, and now anything that comes in will get into the magma ocean until I build up a shield, which is the lithosphere, on the surface. Once I build the lithosphere, any impact will be very hard for that to come into the interior. So how quickly? Well, depending who you talk, depending if the moon during the magma ocean had an atmosphere, didn't, whatever, you can say, oh, well, between 50, 100, or even 200 million years. That's the limit that I will put. So from 4.5 to 4.3 or so is the limit. So they could come as a late veneer of carbonaceous chondrite after the moon formed, or the Earth formed with volatiles. The giant impact didn't strip all the volatiles, and we get this. So when you look at models, this is it's from the group in Nice. This is Walsh. It's called, essentially, doesn't matter what it's called. You have, again, the orbit of Jupiter, Saturn, Uranus, Neptune. And what you will see in here is that Jupiter will migrate in. It's called type 2 migration of the giant planets inside. This is because of interaction of the giant planet with the nebula around it. We will follow by Saturn. They will get into the resonance and they will jump out. And you will see what happened to the material because of the gravitational effect. Jupiter moves in, Saturn follows. Then they got into resonance, come back. Now you have a lot of this blue material coming into, let me show you in another perspective, cross-section. These are the asteroidal belt, Jupiter, Saturn, same thing. They moving in. Then they get into the resonance. I needed to do this myself, and then they do that. So what this model indicates is, well, first it explains the eccentricity of the planets, the inclination, it explains the size of Mars, but also it explains why the terrestrial planets tend to have water from the initial state. So this is a model. It's possible or not, but this is telling me that water could have been there from the beginning. So now, after you produce the impact, why the hydrogen will not escape? Well, there is several models that came out not that long ago, 16, 17. Essentially, you have the proto-Earth. After the impact, you have the proto-lunar disk, that disk of molten material, and then you have a huge atmosphere. The temperature is so high that you have silicate vapor, and it's convecting really, really strongly. Then for hydrodynamic escape, it becomes really difficult for the hydrogen to escape completely, because the convection of the silicate vapor is so strong. There are calculations. Then someone like Palevan did the calculation in 2016 about the possible species that you will get in this atmosphere. The amount of condensation goes, no condensation, total condensation, and how the species will change at the level that this gas cloud begin to condense. the possible concentrations, and this different line will tell you the different density of materials that you had of the surface that make it very reflective, so which allows to keep the hydrogen, and then the fractionation that you would expect for the DH ratio, which is not much. It's a 10 per mil through this process. So all of this is saying that there is a possibility, based on what we know and the models, that during the impact, if the Earth had the volatiles, not all the volatiles should escape. Yes, it could lose the volatiles, but not to a level that completely degas or to a factor of 1,000. So, conclusion, okay? We estimated the amount of hydrogen, carbon, fluorine, sulfur, and chlorine in the lunar volatile classes was equivalent to the mid-ocean rich basalts. Volatile refractory elements ratios in the glasses and melt inclusions suggest that the moon volatile budget is within a factor of 10 rather than a factor of 1,000, more depleted than the Earth. The reason for the discrepancies is that previous work did not consider magmatic degassing, which is obvious. If you take a sample, even on Earth, the first thing that you will do is, how much was degassed before I calculate the mantle? We didn't do that when we did planetary sampling. We showed that the lunar volatiles as air volatile originated from carbonaceous chondrite. The simple explanation, I don't know if it's simple, but one of the possible explanations is that the air had volatile from its birth, consistent with the dynamic model, and either during the giant impact that formed the moon, they were not completely lost, or more volatile were added during the late Venier before this lithosphere formed around the lunar magma ocean. That's it. Thank you very much. Yes.
When you reconstruct the initial water content of the lunar magma ocean, or the moon itself?
What I'm trying to do is, yeah, continue, sorry.
So, the water versus sulfur content, for example, do you see differences with the Earth's mantle? Isn't there more sulfur in the moon mantle than on the
again, that will depend whether you have sulfide saturation, not sulfide saturation, the extent of melting, and all that stuff.
What you see, what yourself you see.
I didn't.
I don't remember.
Okay, the easiest answer I will tell you. Okay, I'm going the opposite way. The simple answer is using the simple graph that I just showed. Maybe true, might not. What is it? Here. If you take just as a bulk, not because it behaved the same, but by coincidence, sulfur behaved like a heavy rare earth during melting. So if you put sulfur, dysprosium, if you do that in many of these earth samples, you will see that they tend to correlate in general pretty well. It's very complex. The sulfur is the most complex of all because of the sulfide, because of the degassing and things like that. But then when I do it on the moon, I see that the difference again is a factor of, that. So at all things equal.
So it means that it would behave on the moon like on Earth.
That's the assumption on mid-ocean ridge.
But mid-ocean ridge is QFM.
Yes.
The moon is low.
Iron was time -1, -2. But again.
Really? Only that?
Well, okay. How you know that
Why
the effect? Hold it. How you know that we said the moon is iron was time -1, -2, right? How we know? Well, how we know that that's the case, and it's not something that as you approach the surface and the surface is vacuum, it produces a change in fugacity of oxygen. We don't know. So I think people have different arguments, but this has been a debate that has been since Ringwood, that he said,
if you degas hydrogen,
for example, no, if you degas sulfur, if you degas sulfur, you can change the redox. In fact, people have worked with metals because they form iron metals.
You degas sulfur as SO2?
For example. SH2. I mean, this is a game, right? You can look for, but what you see, the observation is you see iron metal, okay? Iron metal. So that means that the iron oxide that was in the melt need to get reduced. And then you see iron nickel rounded the iron metal. That means that I now need to decrease, I need to oxidize. I need to reduce, but then from iron to iron nickel, I need to oxidize. So there is a change from reduction to oxidation. That you see, this is an observation.
This is in what sample, sorry?
On all the samples.
All the samples.
Yes.
Okay.
All the samples will have, you need to look for these things, but all these samples will have this iron.
So can't you do that the same as, because you did the exercise with the degassing of water where you say that, okay, I have a factor, I can model this.
I use the same thing for
speciation
sulfur.
factor that tells me what in what species
No,
hydrogen is degassed. Can
okay.
you do that with sulfur?
No. I think, no. Okay, let's go back to that. This.
See.
I never told you how it degasses.
You said that if it's beta.
No, I
you
said
see.
it could go this way, it could go this way, and it could go this way. Now, you want to think what I think, how it degasses. All right. We know that the speciation of hydrogen will change with pressure, with fugacity of oxygen, and with amount total of hydrogen. Okay? Okay, but as I'm moving up, and as I'm degassing, first it's reducing. I might degas H2HD. But as I continue degassing, the total amount of water decreases, so my speciation change from H2DHD to H2O HDO. So it will do. And then if I go to OH, so it reverts, it may do. These errors are just too big.
Really? It really does that?
This,
That's what you
just to tell you that this
That's
is the
what you-
case. I'm just telling you what I think. No, I'm not telling you that's what happened.
So if you do infrared, you should see the speciation.
Oh. Good luck with that one.
Huh?
Yeah, sure, try.
You should see it.
Well, Steve
Let me
already,
know.
Steve already tried, and it's very, very, very difficult to see these things.
Yeah,
Because
but,
Steve is not good measurement.
He's a crystallographer.
So, yes, we try. We still trying to see if we can see the H2.
So how did you get those beta?
This was something that Jim, given all the papers that there were available, that's the guess for the
Because
speciation.
we don't know exactly what it
We don't
is.
know. That's the reason. These are the best guess that we can have.
Okay.
That's all what we can say. Yes.
One of your conclusions saying that volatile, after giant impact, the volatile the volatilization of volatile element is not strong. Is that true for all elements?
What do you mean it's not strong?
No, because the degassing, you don't lose too much element to have water the same and more.
On the contrary. I said on the contrary. I said,
One of your conclusions was that
where?
when you are talking about the
Yeah?
no, it's
Previous?
yeah, previous before.
I don't have any other conclusion.
This one
Okay.
did not evaporate all the volatile away.
This is during the giant impact.
Yes.
This is during the giant impact. If I say, look, if I said, if the moon is 1,000 times more depleted in volatile than the Earth, you can say, during the giant impact, you lost all the volatiles. Because we're saying that the difference between the Earth and the moon is around a factor of 10, the clear conclusion is that during the giant impact, not all the volatiles escape the system. Even when it was a gas cloud, a lunar proto-lunar disk, and a gas cloud, not all the volatiles escape as you would expect if they would be in vacuum. Yes. Make sense?
Yes.
Yes.
No, because for noble gases, for example, we're having evidence that something like 90% evaporate during this process. For
How
example,
you know, hold on, how you know that the noble gases were not evaporated during the magmatic degassing?
this is by, okay, this is the study by isotopic. This is Mukabadai.
Fine.
Where-
Well, I'm just asking.
I'm just taking the same conclusions that to make that volatile. Okay, for I didn't know how we made these calculations, but they show that they compare xenon with helium, for example, and stuff like that.
I'm
So-
saying, yes, there is a big difference. There was degassing.
Yeah.
You would ascribe that degassing during the giant impact. My question to you is, how do you know that the degassing didn't happen, not during the giant impact, the moon formed, now the lava came from deep, during moving up, it degassed and then lie down? How you know that the degassing didn't happen during the magmatic eruption process, not the giant impact? If I take a sample again from the surface, it will be 1,000 times depleted like Francis says. But I'm saying is, before we assume that that depletion is really what tells us something about the interior of the moon, correct for the magmatic degassing, calculate it back, get the initial composition of the moon, then you say how much during the giant impact that degassing happened. Make sense?
Yes.
Yeah. Yes.
I'm not sure to understand your plot when you plot the inverse of sulfur versus grain size. And you make a linear correlation and you infer the composition of the lunar gas.
What you say is whatever is attached to the surface. If you look at the glasses, the volcanic, one of the things that are typical of this lunar, people said, why we know these are not impact glasses and things like that, right? And one of the things that they found when they did the study is that all these volcanic glasses tend to have a coating. It's called surface correlated elements. Very high concentrations of volatiles. These have been measured to a different level of degrees. So the question is how to calculate how much was in there on the surface correlated. You can try to do a measurement, but it's very difficult because it's rounded. You try with the ion probe, it's complicated. So what they did, and this was done by, again, in 1970 something, what they did is look at the same composition of glasses, but with different grain size. So if the total concentration, they put the glasses together, let's say 1 gram. I will get 1 gram of 3 beads, large, 1 gram of 10 beads, medium, and 1 gram of 100 bead, tiny. And what they see is each one is representing more and more and more and more what is on the surface. If you extrapolate to essentially what should be the surface, there is no volume, then you will get a concentration similar to the intercept. Okay, that's, yes.
And this is the data.
No,
No, this is not the data.
What
But this kind of plot has been made for all elements?
No, well,
No,
for
this-
some. No, not for all.
I did not understand the connection between this plot and the last and this plot after. Okay, this is just for the...
Whatever we were able to find. So we tried to build up, right? We got the volatiles, like I told you, meaning the highly volatile, in one way. The intermediate volatile, we tried to get it this way. We tried to work out, it's not by means of,
But
you know,
Alberto, how did
cash it on this, you know, for sure. I'm just saying that all the few things that we did, based on the assumptions that people made before and things like that, correcting for that, give us around this value. For example, here, just to explain the chlorine. One of the things that we did with chlorine, we normalized it, if you see. Oh, come on. No, sorry. Here, we normalize the chlorine with niobium. Okay? Now let me show you something. I know that I'm going way off, but that's okay. The orange glasses have unusually high niobium content. This high niobium content is associated with the high titanium because these have rich in ilmenite concentration. One of the possibilities that this melt pass through an ilmenite layer and dissolve some ilmenite. Then I cannot take this niobium as the initial niobium. We took it as the initial niobium, and then the chlorine went like 100 times more depleted. I don't think that is true. You can see that the yellow glass follow essentially the same composition as the orange, with the difference in the main things that will go to the ilmenite. Then I took the chlorine niobium, this is after I did the figure, on that, and we did this stuff. So there is a lot of caveats that I need to go, and I can, but that's the best we can do right now. I mean, us. Maybe someone else can do it better.
So back to that plot.
Yes.
After you know the surface concentration, how do you go back to the budget?
Well, you go back to the budget only for these elements.
Yeah, but
Because you know what is in the interior, so the melt inclusion,
yeah,
you got the glasses,
yeah.
you got how much is on the surface, then you use the sulfurs to normalize all the others. So you said, for the sulfur, this is the amount. Now, what is the sulfur to sodium, sulfur to zinc, sulfur to gallium, sulfur whatever we were able to find? And then we said, we need to add until we get the value of sulfur. That's, okay, it's just, that we use the sulfur as the measurement.
Yeah, the fixing point.
It's the fixing point.
How much degassing happened during the lunar magma emission?
I don't know. I have no clue. Yeah. That's the
That would
truth.
change your picture.
No, I mean, look, even because it would, do you think that there was an atmosphere or not?
Well, I wasn't there, so.
Exactly. Me neither. Thank God for that.
Qui va sentir primitif.
No, where I'm going. Here. Not here. This. So you have the lunar magma ocean is one thing. And then is this stage, the protolunar disk. So for example, in the protolunar disk, to keep as much water, what I need to do, okay, if you are in a system like that, as this system is cooling, these things, the volatiles, will tend to fall onto the earth because of gravitational, so you have a dry area here, a volatile rich area here, outside, on the outside part. If I condense really quickly, I may trap more, because this is convecting so strongly, I can trap more. But if I am doing it very slowly, then I get into trouble. Because as I condense, the convection begins to cool off, then hydrodynamic escape will kick in. Then the guy that follows,
So the value you give is a minimum value.
the value I gave, in fact I didn't give you, before. This is the value that I get for the moon after all these things happen. Lunar magma ocean, proto-lunar disk. This is what I think we see. Within, it's significant error. But I will give, okay, factor of 2. What we are discussing here is a factor of 200, essentially, between what we said and what people said before. Then Palevan said, well, this is not condensation, this is constant condensation. But then they said, whoa, but these species begin to control when the system is cooling. And then they produce a higher percentage of materials that you can dissolve. The solubility of these guys into the melt is higher than the others. So if I do this, when I'm going cooler, then I can still keep the water. So there are so many things. I mean, look, this is just a model. Okay? You need to tell, well, what are all the thermodynamic variables at these conditions? 7,000 Kelvin. So, but if you ask me how much you lose in each step, no.
A lot.
Pardon me?
A lot.
Well, less than a factor of 10 compared to the Earth.
Yes.
So it's hard. I honestly cannot give it.
Do you think the zinc has composition that was measured in the... No, it doesn't. It could also be explained.
The question was by the magmatic degassing. We tried to run a test, but it failed right now, this year. Essentially, we tried to look at samples that have different vesicularities. assuming that the ones that have more vesicularity will have degassing differently than, and we didn't find any difference. There is a significant difference in the zinc isotope that people have measured, especially people in IPGP. I still think that I think that they see the total. The initial degassing during the impact and lunar magma ocean, and then there is an extra that happened during magmatic degassing. How to, for example, the lunar glasses plot to light isotope, not to heavy, in zinc. The reason that they plot to light is because of this surface condensation. The zinc has been going to the gas, and then when added to the surface, and that gives you light. So I know that there is a fractionation that happened during magmatic degassing. To tell you how much was lost during this stage of lunar protodisk, or protolunar disk, and lunar magma ocean, first I need to correct for that degassing process. That's all what I'm saying. Is considering, before we do anything to talk something, just consider the degassing process that happened, and then, yes, use that value to make a speculation of what happened. Yeah.
In the last year, it has become very fashionable to study apatite and volatile content in apatite from the lunar samples.
Yes. Yeah.
Did they try to estimate, I guess, budget as well, and how do they compare to your glass?
They compare well, but the problem with the apatite is the following. Hydrogen in the apatite is a main constituent of the apatite. You cannot use a simple partition coefficient. Mm-hmm. It will depend on the composition. So what we are
lacking partition coefficient. That's what you mean? We are lacking partition coefficient.
Well, it's more than it's a how you call it?
Terrestrial element?
No. When you do, you need to calculate the K of equilibrium for these phases, and when you do it for iron magnesium, it's not partition coefficient. It's exchange reaction.
Yeah.
So that's what they need to do for the apatite. Now, if I subtract from all and I'd say, given the partition coefficient, yes, it's much higher if you correct for degassing. If also they found very high concentration of some of the apatites, and they found DH ratios that are equal to the Earth.
Okay.
But again, the caveat is...
It was controversial how they estimated.
Exactly. How you get from the apatite that come at the end of the crystallization, you need 99.5 crystallization, that's the melt, and what's the melt composition, and what happened with the chlorine, and what happened with the fluorine in that residual melt after 99% crystallization. Dealing with a crystal like apatite is complicated. That's the reason we just shoot for the glasses, because it's easier. It's easier than the apatite, believe me. Also, imagine that you have different cooling rates. It will affect the different partition that you see because you don't have equilibrium. And it's hard to measure. People measure a factor of one thin section. Okay, just for you to have. One thin section, they saw two groups of apatite. One with the same isotopic DH ratio and a variation of factor of 6 in concentration. And then another group in the same thin section with the same isotopic composition with a variation of factor of 6 in concentration. Or the opposite. The 6 factor of 6 in the DH and constant concentration. So I think that it's telling us that there was water. How much, I think that is debatable, but it was certainly more than when someone said it's 1,000 tons more per liter. I mean, but this is important because we are talking about 200, factor of 200 different. I think that's, to me, I cannot tell you if you say, how much exactly? No, I don't know. But I'm telling you, okay, the factor of 200 is just too big for me.
On s'arrête là?